Good morning and happy Wednesday. I'm Erica Emerson with ONEByte, and I'm joined by Susan Clutter, and of course you all know Scott Fagen. Thank you for joining us this morning for our very first QuickBYTE. For those of you who are familiar with these, they will be very similar to our previous storage bites. They'll be the third Wednesday of the month on a variety of hopefully useful topics, and as always, we welcome suggestions. Before we get started, I want to let you know our next QuickBYTE is June 17th, but back to today. This is an interactive session, and we welcome feedback and questions. Just as a reminder, we're recording this session, so I'll ask that you mute your microphone and when you're not speaking. And with that, I'm going to hand this over to Scott so we can talk about why design matters.
Thanks, Erica. So good morning, everybody. Little conversation today about why design matters, and so that's one way of reading it, or design matters, which are things that are interesting about the design around making something work well on System Z and ZOS. I've been at this a really long time at this point. I actually joined IBM at the time that they were beginning to work on Sysflex and parallel Sysflex. So I've been at this a long time, and I've dealt with many components of the operating system, subsystems, vendor products, IBM products, products that weren't IBM products that became IBM products, and the like. In the kind of the long run of trying to improve availability, reliability, performance, serviceability for customers on the Z platform. The real intent of this presentation is to kind of give you a taste of what you should be looking for when either designing, implementing, or purchasing licensing software for your ZOS implementation. Everybody has pretty much reached the point of Sysflex, with the maybe the exception of the smallest customers who are on their way off. But even those customers, many of the third parties that IBM works with have their own, quote, Sysflex in a box offering, which can really help in managing these systems, certainly to reduce downtime that occurs because of software failures. There's a companion article that goes along with this, and when Erica sends out the slides, you'll be able to click on the link and get to it. It's an enterprise executive, and it came out middle of last month. The obligatory trademarks page, I don't own any of the trademarks. Oh, sorry, Erica, go ahead.
The link also, by the way, is, oh no, please, it is also on the QuickBYTE website. The link to it is also out there.
Okay.
Go check out the check out the their magazine and the article.
So I don't own any of these trademarks, so I have to acknowledge all of them. I will roll right past that. So, sort of this is Applications 101, the anatomy of an application. Essentially, an application sits on a computer. It has some pieces of code that run, whether they run concurrently, serially, they're driven by, as utilities or running as onlines. They all have some set of persistent data that they keep around so that when you stop them and start them, they restart from the point that they ended. They have transient data that's kept in memory. Sorry, persistent data is obviously kept on disk and tape. Transient data is kept in memory to keep the product or pieces of the product in sync while it's in execution. They respond to stimuli. Think of the Kix application might have terminals or APIs that drive it, and they drive actions. They may call APIs. They may drive other programs to run. They may update screens or other outboard equipment. An application, though, is available when its ability to process all of the aspects of it are up to specification. So it's always a potential for an application to not be up at all, right? The program's not running, or to be running degraded. That's not considered available And certainly from the perspective of you as a service provider and your customer as a consumer of your application, it ain't up if it ain't running, and it ain't running to, to what you say it's going to do, right? So nobody likes to go to a web page, their home banking web page, and see, either a 404 or we're sorry, that service isn't up right now. Why don't you try again later, right? That's just not appropriate for many applications. So in the early to mid 80s to the 90s, IBM came up with a concept called Sysflex. In the beginning, there were a bunch of systems lashed together with channel-to-channel adapters talking to each other and sharing a bunch of disk where the applications were stored and the data for those applications were stored, and using coupled data set technology to keep sort of synchronization between the various pieces of those systems. And they would provide the platform for the major subsystems, things like CICS and IMS and DB2, to present a highly available platform which spread across multiple or at the time MVS instances running on multiple System 370XA and 390 hardware. And this was improved over time, through the 90s into the 2000s, into something that's now called a parallel Sysflex, which introduced additional technology called a coupling facility. And also improvements to the link technology, improvements to the way programs could interact with the system, interact with various subsystems. So there's a lot. I don't know that it's the same amount of investment that IBM put into to create the original 360, but it was a tremendous amount of investment in both the hardware transitioning from large water-cooled machines to much smaller CMOS-based air-cooled machines, which of course today are now optionally water-cooled, and being able to keep a couple of systems together to a highly virtualized environment where up to 32 different ZOS images can be working in concert with each other. Parallel Sysflex is really it's a shared everything architecture. You have at least one instance of the software fully active on every LPAR or every system in the Sysflex. The state data is shared across software instances. That could be through the use of shared disk, shared files, coupling facilities, and the software instances are aware enough of each other so they can react to the failure of a piece of them. Whether that failure is because the software failed, because an underlying piece of the operating or system or subsystem fails, or an entire piece of hardware fails. So kind of pictorially here, I have a two-system Sysflex with two racks of DASD that are, one's the primary set and the secondary set. To keep the picture from being excessively busy, I didn't show any of the connectivity, but figure that all of the systems are connected to all of the DASD, all the systems are connected to all the coupling facilities, so everything is shared with everything else. And in this picture, right, each one of the application instances is running in an instance of an application server, which is Sysflex aware, talking to a database server, which is Sysflex aware, and has a set of data that is associated with the application server and the database server at a coupling facility, which is accessible to all of the instances of that application and database serving running on other systems in the Sysflex. This is highly scalable, right? You can go to 32 LPARs in a Sysflex, spread over some number of pieces of hardware servers, that's obviously 32 or less. And the coupling facilities can be LPARs within the same physical hardware, or they can be external. There's also timing, the Sysflex timer, or now the new timing boxes, which allow that all the systems are kept in a synchronous and a consistent time source, so that each of the applications or application serving pieces can understand the sequencing of events down to a very, very low level of discretization. The net here is that if any individual piece fails, the rest of the application serving pieces move on with minimal impact. So if I lose an application server over here, I lose nearly no capacity because the other application server here will just simply grow to use the CPU that was being used by this application server. Same with the database servers. If this database server fails, this application server will stop processing, but this one will keep going while these pieces recover themselves. For shared data in the coupling facilities, this is replicated through some method of duplexing, whether it's system managed or user managed. So all the application data that might be written over here is replicated over here. There are optimizations that allow these LPARs to read from the secondary copy transparently so that everything runs at maximum speed, maximum availability. And if, say, you are one of your pieces of hardware needs to go down for maintenance or it does fail in that rare event, this server will continue to run, albeit with less capacity. But if an LPAR fails, the other LPAR, if you judiciously set up the sharing of the processors within a box, this other LPAR can grow to take advantage of the CPUs that are no longer being used by this failed LPAR. So there's a great deal of
one-to-one
and design. Sorry, is it one-to-one? Is it one-to-one? One-to-one what's?
Like mirrored, right? It's an exact copy.
Oh, okay. Yeah, each one of these systems is as similar to the other as possible. So there are many services within the operating system and the subsystems. These are essentially clones of each other. So LPAR 1, LPAR 2, LPAR 3, and LPAR 4 all look almost identical with the exception of names, right? And you might even call them LPAR 1, LPAR 2, LPAR 3, and LPAR 4, but their underlying configuration under ideal circumstances is as similar as possible. So if you have set up, say, this LPAR to share all the processors, when you can tell if this, say, there's a 500 MSU CPU, and you could tell ZOS LPAR 1 that he's allowed to max out at 500 MSUs. You tell LPAR 2 that he's allowed to max out at 500 MSUs. At no point in time can either of them, reach or exceed 500 because the whole box is only 500. But if LPAR 2 fails, LPAR 1 will grow to use the capacity that was being used by LPAR 2. And now with the new system recovery boost feature, one can use spare capacity that's in the box that you may not have purchased to bring LPAR 2 back, which is kind of a cool feature as well. So it's set up for high performance, high availability, high scalability, and certainly high parallelism.
Right.
So I harp on this. I harp on this stuff very, very heavily because really the design principles are no single points of failure, and try to make everything work as much as it can, looking like a single system image. Right? The underlying ZOS and subsystem human interactions, system interactions that are available almost are transparent. Now, you may need to send a command over here because there's something going on over here, but many of the system commands, many of the subsystem commands, you can issue them anywhere and get the same answer out of all of the various systems. Doesn't matter where it runs. And some commands will run everywhere to get you a result. So these are the key takeaways, key points. One of the things that I did when I was IBM was I was the parallel Sysflex approved person for one of the people. I can't say that there was just one. And other parts of IBM and software vendors would send glossies or information about their products to get this sort of parallel Sysflex approved stamp on it, sort of like being Azure approved or Amazon approved. And I'm going to talk about some of the ways that these products tried to get away with being way less than the minimum required and did not receive, parallel Sysflex approval, at least from me. So the question becomes, right, you've built, as an operations person or as a data center person, you've built the best you can build with great hardware, great underwear, operating system, and, and low-level middleware like Jez. great middleware like MQ Series, DB2, Kix, and IMS. But if the application isn't exploited, what good is all that? I mean, I heard this over and over again in the mid-90s because IBM was selling basically parallel Sysflex to the data center management team who build it out. But when the applications aren't taking advantage of it, they're not getting that 5 nines or 7 nines of availability that they were promised. And
right,
that's because
applications go down anyway.
Right, they go down, and you still are being leaned on to get them back up. And you don't get the scaling abilities and the scaling capabilities of the platform where you're only running one copy of the application on one box. So in reality, right, we're now 30 years into this technology. Outside of the base operating system, Kix, IMS DB2, WebSphere, and CA MIM resource sharing, and I'm willing to be told that there are other ones that are out there, but these are the ones that I'm highly aware of. Really, very little has been done in the overall portfolio of software from the IBM and the software vendors that really supports this level of availability in the platform. And this failure to act does reduce your ability to provide a reliable platform and to keep it up and running, even from both unplanned failures and planned outages. Yeah, I'm gonna harp on this, right? This technology is not new, and it's definitely not unstable. It's been around since 1990 when base Sysflex came out with MBS 4.1 and parallel Sysflex came out in MBS 5.1 in 1994. I mean, if you're on the platform at that point, you've been around a long time. So what's happening is software vendors are actually leaning on you, their customers, to manage their product's deficiencies. So who suffers when local automation goes south? Because that's typically what a customer is going to put in place around, say, their job scheduler that runs on one system in the Sysflex, or their automation product that focal points all the events to a single system in the Sysflex. You can't possibly react fast enough with human operators, so you're going to build a bunch of local automation to detect when that underlying product fails and hopefully get it restarted, recover and restarted. But who's going to suffer when that automation goes south, right? The vendor's going to say, well, your automation didn't work, but you should be able to push back and say, but your product is not supporting the key design principles of the platform. So there are kind of 3 usual suspects in how these products are built. The first one is what I call Sysflex unaware. You just run the application independently everywhere. Now, this is a viable option for many products, right? If you've got a sorting product, it just doesn't really need to understand that it's running in a Sysflex, right? It just needs to have access to the data that it's sorting. But a job scheduler, which is scheduling jobs across the Sysflex or even beyond the Sysflex or multiple Sysflexes or to systems that are, in the distributed world or in the cloud, many of them run on a single system and, kind of lean on the other systems in the Sysflex to do very little. That's sort of this phase 2, the focal point idea. And then what they'll do to go one step further is to lighten the load on your automation needs is they'll create this idea of a hot standby, where the focal pointing system does all the work and the hot standby just kind of stands around with its hands on its hips, tapping its heels, waiting for the focal point system to fail or the software to fail. And then it will do what it can to recover whatever data was in flight and restart it locally. And then, of course, it may or may not be up to you to, get back to the original focal pointing system and move it. Now, one of the, kind of the key issues around these is that it makes your life harder as a systems administrator, systems programmer, data center person, because now you're kind of arranging automation for each of these individual products, and that automation has to work between products. And you now have to build operating principles for the people who are operating these systems to understand where this stuff is. So, we talked a little bit about Sysflex unaware before. This is just sort of the enumeration of the pieces. I've seen a number of products that are systems management products that do actually force the administrator of that product to periodically gather data from all the instances of the product and combine it with the utility and then spread it back out to all the pieces of the product so that it runs again. It's highly it's difficult. it means you're just basically leaning on people to make the product do what it ought to be doing automagically. I mean, the systems are all connected. They share DASD. There are many underlying programming services to make this stuff go. And the fact that the software vendor hasn't made these changes, I think says a lot about the viability of the product for the long term. Right, the focal pointing issue, more than just the systems management, you have to know where the product is running. You have to account for the fact that in a unplanned outage, there has to be a way to get the product moved to another system. And in a planned outage, you need to be, very carefully set up the procedures to be able to move the product so that you can maintain high availability. I don't know, many places run job schedulers like this, where when the system that's running the job scheduler needs to be brought down for maintenance, or even the product itself needs to be brought down for maintenance on particular systems, you have to pick it up, move it someplace else. And if you're, if you're doing this either during the production day or during the batch run overnight, how many jobs are delayed and not started potentially in time, thus extending the batch window or breaking your SLAs while this application is being moved from one place to another. This also has
a manual problem.
Lots of manual. It also has large implications around scalability. The system that's running the application is naturally going to become more and more busy the larger the other systems are in the Sysflex, or if you add systems to the Sysflex. So if you look at the kind of the graphic that I have here now, I have 4 equally sized systems running this, that are sharing the functionality of this application. If I wanted to bring another system into the Sysflex, I'm now adding 25% more work to that application. What is that going to do to the other things running on LPAR1? Will it potentially eat LPAR1 alive? Will it add latency because there is some set of serialization going on because the work is all being stored and forwarded back to that application? If actions have to be taken on LPARs 2, 3, and 4, that implies that a message goes from, say, 3 to 1 and then 1 back to 3. That adds latency and could potentially impact workload or SLAs that are occurring. It's still it's not ideal, right? Because what you're not doing is, like, probably use this term a little bit too loosely, you're not peanut buttering the work across the Sysflex. If LPAR3 got in the ideal world, if LPAR3's system got very busy doing work for this product, only LPAR3 would get affected. Here, LPAR3 and LPAR1 will get affected, plus the underlying Sysflex componentry that's moving all that data around is going to see an increase in utilization as well. Finally, the last really big issue becomes what happens during a failure. If all the work is being forwarded to LPAR1 and LPAR1 suddenly fails, what happened to all the work that was in flight? Is there a way to recover it? I don't know. I mean, that's between you and your software vendor to figure out. And if you don't recover it, what happens in the long term? Right. The focal point with Hot Standby is essentially similar, other than they provide you the magic of moving the application, say in this case from LPAR1 to LPAR3, should LPAR1 fail or the application fail on LPAR1. All of the scaling problems are still there. All of the latency problems are still there. And interestingly enough, what if your agent in Hot Standby happens to be in the same physical server? Say it's not an LPAR3, but it's an LPAR2, and there's a CPU hit on server number 1, so that both LPAR1 and LPAR2 go down, thus taking your application in Hot Standby out. You have to provide for some sort of automation to either detect that situation has occurred, or hopefully the product has built-in detection to say, I don't want, add the application and Hot Standby to be failure unisolated, right? There's a bunch of services within the operating system to tell you if 2 particular pieces of work are failure isolated or not. Again, right, if you're going to go this far, you might as well do the work to make the application work correctly in a parallel Sysflex environment and take the sort of take the stupid human tricks out of your hands as the administrator customer of these products. So one of the things that I've heard from product managers not just in ISVs, but at IBM themselves, is they'll say, well, but these are, they're second tier applications. And I would respond with, if they're second tier applications, they seem to be highly entwined with your first tier workload, right? Your job scheduler is scheduling, utilities, sequencing things that need to run, and sometimes those windows are very tight. Your automation product is watching for things to go up and down and, times of day and, making sure that things are occurring in the right order. So if they're not running, your application is incomplete and could be compromised in terms of its availability to do work that might not be exactly right now, but might be in a few minutes, a few hours, or a few days. The question becomes, how long can your applications or your environment wait for a delay in any of these products while your automation or your people are recovering them from a failure? And of course, right, who's the throat to choke when the SLAs are breached, right? You can't go back to an ISV, I won't mention one because I'll get in trouble. But, when your SLAs are breached due to a product failing, whose throat is it that gets choked, right? Who doesn't get their bonus or who gets penalized? It certainly isn't the ISV. So kind of to conclude here, a chain is only as strong as its weakest link. You've invested millions of dollars in hardware over the years, millions of dollars in software. The application team has updated the applications for high availability. If you've built out a GDPS or a GDDR, you're really interested in having 7 nines of availability, right? You can get 5 nines without GDPS, GDDR, which is still phenomenal. It's kind of like 2 or 3 minutes a year. I think 7 nines is maybe a minute a year of outage. This investment really does demand that you lean on the people who are selling you software to not be the weakest link, to not snap, right? Now you're holding this great, 2 great pieces of chain instead of 1 in your hands when all hell's breaking loose. These are hard conversations to have with these software partners, but you're spending good money, and you shouldn't be spending good money after bad. If they are impeding the ability of your environment to be high availability. So that's kind of the end of the story for me. I would really say, spend some time with the article because I put a lot of details in there. There's a ton of reference material that I point to that talks about all of these facilities and what you can get out of them and why you should do them. Clearly more than I could do in a 20-minute or half-hour slot on on a Wednesday morning. But thank you so much for your time and attention. I really appreciate it.